In this series of videos I'm attempting to repair this PDP11-34A vintage computer. In the first two videos in this series we looked at the basic machine, tried to power it up, didn't do anything, there was nothing on the display, wouldn't respond to any key presses, and so I started removing cards and ended up with just the console and bus terminator card in the CPU backplane, and it still wouldn't come to life. So something was obviously very wrong with it. It was clear that the console and its control interface weren't working, and so that is what I decided to repair first. So in this video I want to get this console working, and as you can see I've removed the CPU backplane, separated the power supply. I've got just the console control card plugged in along with the console display and keyboard. Now it won't run like this, the board won't start up. I'll explain why in a few minutes, but this is based around an Intel 8008 processor. Very rare, very hard to get hold of, so I want to be very careful with this. And so I've actually been through some of the repair already. I haven't videoed it, so it's quite difficult working around the camera, and I didn't want to blow this up. I'll go through what I found and then explain a bit about how this works. Before I get on to that, just to address a couple of comments. Someone said that I'd said, and I've said it in this video, this was made by DEC. It's an abbreviation, and they said no, that's wrong, you're supposed to say DEC, tongue-in-cheek, but yeah, that's the way a lot of people pronounce it. But I'm not a big fan of speaking abbreviations, and especially when making videos, if it's an abbreviation I will normally spell out the abbreviation and not state it as a word, simply because I'm trying to make the videos as clear as possible. And if somebody's not familiar with the machine or DEC, then the word DEC might not really help them. Also, somebody else said that they were a bit concerned about my little on-off switch here, and this is what I'm using to remotely power the machine on or off. This really duplicates the functionality of the knob on the front of the console. But don't worry, this is not passing the supply current, this is just connected to the remote control input on the back of the power supply. It's only passing a few milliamps, it's just the control signal that instructs the supply to turn on or off, in the same way that the main power doesn't flow through this switch either. Okay, so onto this repair. As I say, I've been through some of this repair already, and I'll go through what I found, some of which I kind of glossed over in the previous video. I was looking through and testing the power supplies, so we were going through and testing all these supplies and noticed that the 20 volt rail wasn't there. Now if you look at the schematic for the power supply in this, which incidentally you can find online, just search for DEC11-34 and you should find several versions of it. If you look at the power supply schematic for this, you'll notice that the 20 volt supply is actually controlled through the same part of the system that provides these bus DC and AC low signals. Now what these two signals are for are to instruct the main machine if the power supply, either the AC has failed or then subsequently the DC will fail. So if either of those two show any problems, then it allows the main processor time to shut down gracefully without destroying data or doing any damage. So the way this system works, it's very similar to the way the bus works. In fact, it is part of the bus on the DEC, or the PDP machines. You need the terminator card in these, as I mentioned previously. So that's one of these. This sits in the end slot of the backplane. Now it's not really a termination card in the normal sense that you'd use these days, where it's there for signal integrity purposes. It kind of is, but it's really there to provide pull-up resistors and load resistors for the lines on the bus. Most of the cards that you plug into this, all the inputs and outputs are effectively open collector, and what it means is you can plug multiple cards into a common bus and it won't do any harm if two of them fight for use of the bus. It won't work properly, but it won't do any damage, because the high levels are provided by pull-up resistors. If one card is trying to go high and one's trying to go low, then all that will happen is the one that's trying to go low will pull the line down through the resistor. And it's quite a nice system. It does limit the speed it will run at, but it is quite nice. Unlike tri-state buffers, which if two are enabled at the same time, they can damage each other, because if one's trying to drive high and one's trying to drive low, then that's a different situation from having two open collector outputs connected to a common rail. So the bus low, DC low and AC low lines are common collector output style drive signals that come from all the regulator cards, and also certain other cards. It's fairly rare that they're used explicitly as control signals, but the lines, the control for the lines, can come from any one of several sources. And what I didn't show in the previous video is that the bus DC low line was staying low, even with the termination card in there. And that's obviously a bad sign. It means the system's not going to start up. And I did effectively correct that when I was trying to get the machine to work and got it to come high. I'll explain how in a minute. But it still didn't do anything. It still wouldn't start the machine up. And the same is true when I had it like this. Despite getting the line to go high, it still would not start up the console. So what I found initially, and the way I got the line to start going high, was it was very simple, and I found this when I was taking the system apart. These connectors that connect the backplane to this distribution card are a real pain. They're the same type of connector that you get on the power connectors on more modern PCs. And anyone that's tried to use them will know they're a real pain, because the pins just kind of waggle about all over the place. And when you're trying to get it into the mating socket, they don't always line up and you can't push them in properly. And that's bad enough with a 4-pin connector like you get on a PC power supply, but when you're getting 15 or 20 way connectors like you get on these, they are really a pain. And what I found is on one of the connectors, one of the pins had been kind of bent over. It wasn't bent over completely, but it had gone down, or tried to go down the side of its mating receptacle rather than down the center of the female pin. And it had prevented the socket from being pushed all the way in. That in turn was preventing the power supply from working as it should do. And this is the connector between there's a kind of a mains module input that plugs into the back of this main supply. It was one of the connectors between that and the power distribution board, and it was preventing the power supply working properly, and it was sensing it as a problem, and it was holding the bus DC low signal low, and if it doesn't release that and allow it to go high, then this system will not start up, and that includes this console. So I fixed that and fitted the without the console control card. I fitted the termination card, and then the bus DC low and AC low lines were behaving themselves, and they were both going high. Now it won't do that with as it's currently set up, because I don't have the termination card in, so there is no pull-up resistor on the bus DC low or the bus AC low or any other line, so it won't work. And that was intentional. I didn't want this card starting up. I didn't want the chance of damaging the 8008 processor. What we can do, however, and what I did, I'll go through now the process I went through. I've already been through this. I did it off camera. As I said, I didn't want to damage this fairly rare device. So step one was to power this up and test a few key voltages. Now this is a bit odd in the way they've designed this, in that there are some intermediate voltages, and they are derived either through resistor diode regulators on this board, or in some cases, as one stated here, 3 volts, and that's just derived from a pair of resistors from the 5-volt rail to ground, and we need to measure that and make sure that those voltages are all present. It won't start up because bus DC low is low, it's got no pull up, and if we look at the schematic, you notice that you probably can't see it, but it says bus DC low here, and this just prevents the 8080 from starting up. I'll come back to this in a few minutes, but I'll explain why it stops it starting up. But the first thing I want to do is power this up and see if the required voltages are present. Now if you look at the schematic, all the ICs are identified through an E and then a number, so this one's E17, E16, and if you want to find those on the board, they're numbered from the bottom right going up, so it's E1, E2, E3, E4, E5, E6, E7, E8, E9, etc., and you can just count along and find the particular IC that you're looking for based on the diagram. So the first thing I'm going to do is check for the 5-volt supply, and for this 3-volt supply you can either check it at the pin of one of the appropriate ICs, E12 for example, which is this one of course. In fact, on the top row they are labelled, so it says E12 here, so it's E6, E12, E18, so it's a good starting point. If you want E26 for example, you've got E24, 25, 26, so it's this one. That's why they're running numbered across the top. So what we'll do now is check those two voltages. We should have 5 volts on one of the power pins of one of the TTL devices, except the ones that are driven from 3 volts. And this 3-volt divider chain I mentioned is this one, these 2 resistors in the top right hand corner. One other thing I did initially was power this up and then watch it for 5 minutes through the thermal camera and just make sure nothing was getting hot. Okay, before we get started, there's nothing exciting to see in the power supply, so I'm going to move the camera across so you can see a bit more clearly what's going on with the scope and the multimeter. So hold on. Okay, so what I'm going to do now is power it up using the remote control switch. Okay, it is now on. It's very quiet because the fans aren't there. And we'll get the multimeter and we'll test the voltages. So we'll test the 5-volt rail and see what we're getting, 5.16 volts, you can see on the meter, which is fine. And if we check this dropper, we should be getting, it says 3 volts, but it's 4 volts. It's basically something less than 5 volts is what we're looking for, but more than about 2 volts, so that's fine. So the next thing we'll do is look at the pins on the 8008 processor. The first one we need to look at is the clock. So we'll actually start off looking at the clock signal. There is a test point for this, which is this test point up here, test point 1. And if I get the scope probe and connect it to test point 1, what we should find here is a 1 megahertz signal, and this was missing. There wasn't a clock when I first started doing this, so let's adjust the scope. So the scope sets to 400 nanoseconds per division. You can see we've got a nice clean clock there. As I say, that clock wasn't there, and that was this IC. I replaced that, and that brought back the clock. The board still wouldn't start up, so I had to start looking at other things. Now, if you're not familiar with the 8008, it's a bit of an odd ball processor, very early of course, so we can't really criticise, and it was the real beginnings of the way modern processors work. If you've read my book on the transistor processor and how a processor works, then you'll know that processors generally have a multi-machine step cycle. That is, they require several clock cycles to perform a full machine cycle. And in most processors, those phases are internal to the device, so you don't have access to them. And I go through a lot of detailed explanation in the book as to exactly what each phase is for and how processors use phases to control the overall operation. But in brief, what they do is, as the clock is applied to the device, each cycle of the clock steps the processor onto its next phase, and each phase is responsible for carrying out certain parts of an instruction cycle, such as fetching data, writing data, that sort of thing. So it's kind of a multi-step process, but all carried out through a series of phases. Now with the 8008, we have these control pins down here. There are 3 of them. There are 4 control pins, but one's a sync pin. The 3 control pins that are S0, S1, S2 are really the phase output pins, because all the decoding and control logic to drive the 8008 processor is done externally. So for example, connecting to ROM or RAM, setting the address, this sort of thing, is all done through various phases of the processor, but it's up to the external circuits to deal with that. And if you look at the spec sheet for the 8008, you'll see how these 3 signals change through each machine cycle. And also notice that we only have one 8-bit bus. There's no address bus. Well, there is, but it's internal to the device. But there's no external address bus. So with the 8008, each machine cycle starts by outputting the first 8 bits of the address. It has to be latched somewhere by the external circuits, using the phase signals as the key as to when to do that. That's followed by 6 more bits of address and 2 mode bits, which are used to determine the mode of the particular instruction being carried out. So in this particular design, we have this pair of buffers, and they are used to determine, especially it's a multiplexer and buffer, bidirectional buffer, and this determines which direction the data or address is going and what the source or destination is. Obviously without the clock working it wouldn't do anything at all, but what we should find is that when we look at the these 3 pins, so they're pins 11, 12 and 13 on the 8008, we should see them going through a regular sequence. Now I know it's not going to do that, but we'll have a quick look. I'll just show you what's on those pins. So if we look at pin 11, notice that's low, pin 12 is high, and pin 13 is high. Pin 14 is the sync, and that should always be present as long as the clock is running, and it is. Then we have the 2 clock inputs, which are out of phase. You can't tell, I've only got a single channel connected, but they are 2 out of phase signals, and they're both there. But nothing else is happening, and then it wouldn't be because there's no activity on the phase signals. So these data bus, which is what we're looking at now, is inactive. Now this is to be expected because if we look back at the schematic, and it will vary depending on the design of the system, but here we have the clock generator, and this is just used to generate the 2 phases of the clock, and then we have basically a keyboard clock output, and we have this part of the system down here, which is part of the interrupt. It has a single interrupt pin. And it's, as I say, it's a bit of an oddball processor, because to get it to run, what you have to do, when you first power it up, it will go into this weird state where it's kind of in a, it's held in limbo, it won't do anything, and you have to toggle the interrupt pin. And if you don't toggle the interrupt pin, it will just sit there indefinitely doing nothing. But if we look at the circuit, we'll see that this circuit here, which is responsible for that startup action, is actually controlled by the bus DC low signal. And so if the bus DC low signal is low, it disables this circuit, and it will prevent the processor from starting up, and that's intentional. It's to stop this running if there's a fault with the supply. And also when the supply shuts down, it will do the same thing, it halts this processor. So with that said, it meant that with the bus DC low permanently low, it wasn't ever going to start up. So I corrected the fault with the power supply that was causing the bus DC low to be held low, and this still didn't start up, although I could then see the interrupt line toggling when I powered the machine up. Clock wasn't running, got that working. That was this device up here, sorry, this one, and that then restored the clock. It was kind of then working, but it still wasn't working correctly. I then just found a dry joint on one of the ROM chips, corrected that, and we seem to have made some progress. So currently it's powered up, but you can see it's not running, there's nothing on the display. But what I can do, without going to the trouble yet of turning off and fitting the bus termination card, is we can fool it into thinking that the bus DC line is high. So if I connect a resistor across these 2 points, notice that the display comes on, and so this board is starting up, which means that if I turn this off, I can now fit the bus termination card, and in theory this should start working. So I'll get that fitted. Okay, I fitted the termination card. We don't need the grant cards or anything else in here. We're just trying to test the console interface and the console itself, and it runs as a standalone system. Has to do that if you think about it. If it relied on the main processor, it wouldn't be able to have overall control. So this really it allows full bus cycles to be put onto the bus to read or write to various registers, and that's how we can make use of this to fully test the system and various cards within it, as long as we can get it to run. For now, power this up, and again I'm using the remote switch here, but I could turn it on now with this knob on the console. But I'll switch it on, and hopefully you can see that the display has come on. Not only has it come on, but it's read set to 0. Looks like we have a faulty LED, 7-segment LED there. It's unlikely to be the driver chip because these are multiplexed, so they're all on one at a time, and so the same line that's driving the segment that's out is the same line that's driving the same segment in the other displays. I also notice we now have another light on, so that's the bus error light. That's not surprising because we don't have a termination at this end. There's no other card at this end of the light of the bus, so we can just clear that. Okay, so there are proms in here, and they contain code to enable us to do certain things, and there's also some scratch pad RAM in here, a very small amount, that allows the storage of the value you type in on the keyboard, as well as a value that's read from the bus, and then you can decide if you want to look at the value you've just read into this internal memory. So it's a fairly straightforward system. It contains enough circuitry to generate the control signals, to generate a full cycle on the PDP bus. It allows us to write data to a device or from a device at a specific address. We can then use this card as a kind of standalone test tool, plug in other individual cards without the main PDP processor, and then we can write to and from various addresses. That includes the address of the scratch pad memory in the controller itself. So that's what we're going to do here. All I've got plugged in is the bus termination card and the console interface control card, which I think is now working. It was a much easier fix than I'd expected. I was expecting this to take quite a while to get working, but I want to see now if it's working correctly. So the first thing we have to do is get to the part of the code in the console where it's going to allow us to control the main backplane, or at least send cycles up and down the main backplane. Even though we're not going to do that explicitly, everything we're doing at the moment is on this card, we still have to get to the same part of the code. So the first thing I have to do is put the card into the correct mode, and this is to try and get the card into the correct part of the firmware running on the system that is going to allow me to read and write values to the data bus. So we just go through the diagnostics program. I'm getting a bus error light coming on, but that's because I don't have a terminator at the front end of the backplane. So we'll clear that. What we can now do is try and enter a value into the internal memory. Going through that diagnostic has taken us through to the correct part of the system, and what we should be able to do is enter a value. So I'll put in 4, 5, 6, 1, 2, 3, and that's now shown on the display, 4, 5, 6, 1, 2, 3, albeit with a missing segment, and we can now load that into the internal register. Okay, so that's what we've done there. I should now be able to read that value back by examining the address for the internal register, which, as I said, is at 777570. And I've now entered that as an address, and if I hit the load address key, again it zeroes the display, but it should have loaded the value from the internal register at 777570 into the display register of the control card, and we should now be able to examine that, which we can. The end digit is showing as 0, but that's because it's outside the range that's allowed. So if we put in a different value, so if we try putting in, for example, I'll clear this, I'll put 1, 2, 3, 4, 5, 6, and we'll do the same thing. We'll load that into memory. We'll then try and read this back, and we'll try to examine that and notice that we have the correct value. So it does appear to be working, and it was a fairly simple repair in the end. It was just the clock circuit wasn't working correctly. We had a dry joint on one of the proms, and the initial fault that was locking up the system and stopping it getting working was just caused by a faulty connector, or at least the connector hadn't been inserted correctly. So a fairly simple fault. If the rest of the machine goes this well, then I'll be quite happy. So the next thing I want to look at is the missing segment on the display. What I'll probably do to start with is just swap the N1 and this one. It'll do for now, and I'll try and find a source for matching display. Of course, if I just change that one, they're going to be different unless I find an exact match. The other thing I'm going to do before we finish is just see if the switch on the console can be used to power this up, which it can, and it should do exactly. This does exactly the same thing as the remote switch on the back of the power supply, and this should put us into exactly the same mode as we were before. And it should allow us to do exactly the same thing. And as you can see, that works just fine. So again, not quite as complex repairs as I'd expected, but these are fairly simple to work on. The 8008 is a particularly nice processor to try and fault find with, because you have access to the external phase signals, and that means you can look at exactly where it's failing to operate. And in this case, it just simply wasn't starting up, and then it couldn't properly read the data from the PROM. What it was doing, incidentally, when it had a dry joint on the PROM, is it would come up with all zeros on the display, as it should do when I first powered it up, but when I pressed the key, the display went blank and wouldn't come back on again until I power cycled the machine. And as I say, it was just a dry joint on one of the proms, and it was obviously just returning the wrong instruction to the processor, and it was not liking that. The bus error we keep seeing is because there is no front card to terminate this. You can put another one of these termination cards at the front, or really any card that's going to give a proper termination and response to the signal on the bus. Because we don't have that, the signal is getting to the end of the bus and then it's just stopping, and that's what gives us the bus error. Okay, well, I hope you found that interesting. If you want me to go into more detail on these repairs, let me know. I try to avoid getting too bogged down. I know some people like the videos to move along fairly quickly. If you want more detail on this, let me know. If you want me to go over some of the cards in more detail, let me know. This one in particular is quite interesting because, as I say, it is a standalone microcontroller, microprocessor system in its own right, and it does work kind of as an annex to the main PDP system. So in the next video, what we're going to do is start looking at some of the cards and using this setup to test those cards. So before I go to the trouble of reassembling the PDP, what I'm going to do is test a few of the cards, such as the serial cards, and what we can do is plug it in, do exactly the same as we've done here, except writing to the addresses for the control and data registers of the serial card. We don't need all the infrastructure that the PDP main processor needs, but we can still fully test the cards. So by the time we get to reinstalling the PDP CPU cards, we'll have a fairly high degree of confidence that the other cards that we intend to use will work, and we're not going to be chasing multiple faults. If it's always a case of, well, if there's no serial data, is the fault with the serial card or is it with the CPU? So doing it like this means that we can kind of separate those two things, and this will also allow us to carry out some very specific testing, and if we need to, we can put a scope on the cards, and it also means that we can put the card at the front. It doesn't need to be at the other side. So this is just generating a bus read-write signal system, so we're not constrained by the same requirements as the usual PDP system, and so if we want to, we can put the card we want to work on at the front, get full access to it, and that will make life much easier. So in the next video we'll look at one of these serial cards, try and get that working, connect it to a remote terminal, and see if it works, and how we can use this setup to go about testing it.